Yeah, as of now, we have discussed about binary adder, binary subtractor, where we consider half adder, full adder, half subtractor, and the full subtractor. And we also discussed like how we can design a 4-bit parallel adder, binary parallel adder. Okay. Now the next arithmetical operation that we should know is the binary multiplier. Okay. So how the binary multiplier works, and we will check it out how we can design the circuit for this binary multiplier. For example, I have 2 bits, something like this. Let us assume I have 2 numbers, which is x1, x0, and the second number is, let us assume, y1 and y0. Okay, if the number is something like this, and I want to multiply these 2 numbers, so how we can do that? To do that, we can simply follow the procedure what we generally consider for the decimal multiplications. Okay, so in decimal multiplication, we used to start from the right hand side, and then we used to multiply each digit one by one and then try to sum it up. Okay, the same process will be followed, especially if I am considering for the binary multiplications. So let us try to see quickly how we can do that. So suppose I have a number like x1, x0, and I want to multiply it with the y1 and y0. In that case, what I have to do? I have to simply follow the simple procedure what we have to do. I need to multiply with like y0 will be multiplied with the x0. So this is the first section. Second term will be like y0 will be multiplied with the x1. So y0 x1 will be there. So this is all about how we can do the multiplication with respect to y0. Now I need to consider y1. So I will multiply this y1 into x0 and then y1 into x1. Okay, so y1 into x0 will be here, and y1 into x1 will be here. So this is what we will get the numbers. Okay, we know that. Suppose if I'm talking about, yeah, before we can conclude all these things, this is really very important. Suppose if I'm multiplying 0 with 0, so I will get 0. 0 multiplied with 0 will be 0. 0 multiplied with 1, this will be 0. 1 multiplied with 0 will be 0, and 1 multiplied with 1 will be 1. So this is what we know these things. Okay, now what is the next step after this multiplication? This term will be replicated as it is. Second term will be like, yes, because we are replicating this term as it is here, so there will be no carry generation over here. So none of the carry will be generated, no carry. Okay, so no carry will be generated from the first digit. Now if we talk about the second digit, I have one number, this one, and I have this second number, and I need to add these 2 numbers. So can anyone tell me, to perform this operation, which kind of circuit I need to use? Adder circuit. Definitely I need to adder. So which kind of adder will be sufficient? Half adder or full adder?
For full, if there is carry.
Yeah, let me explain it, then I will ask the question, right? Please let me explain first. We know that from the first digit, there will be no carry in the same digit that will be reflected as a P0. Okay, product bit 0. Now, because there is no carry at this point. Now, if we talk about the second bit, then I will have this number, I will have this number, and I need to add these 2 numbers, and the sum will be reflected as a P0. And because we are summing over here, some probability there could be some carry over here. So carry is possible at this stage, but carry is not possible at this stage. Okay, so now please tell me which kind of circuit will be needed.
Half adder.
Half adder will be sufficient for this purpose, because we are adding this number and this number, so sum will be there, and there may be some carry, because see, might be this will be 1 and this is also 1. So 1 plus 1, that will give you 0, and carry will be generated. So this is the chance. So the carry will be generated, and that carry will be forwarded over this point. Okay, now whatever the carry we have here, this will be forwarded, and I need to sum this carry with this number, which is x1 and y1. Okay, so for this purpose, which circuit is needed?
Full adder.
Full adder. Why full adder?
The carry is generated from the previous.
No, but the carry is generated,
But
but
only two inputs are
only two inputs
coming.
are there,
So
right?
half adder will also work.
Yeah, so half header will be sufficient for this purpose. So half header will be needed. That will give you the sum P2, and the carry which will be generated, that will be forwarded as the P3. Okay, so this is what we need. Now let us try to see what kind of, how many logic circuits are needed. So as of now we saw we need two half headers. Okay, one half header for this purpose, and the second or half header for the carry which was forwarded from here and to add this number. So two half header is needed. What other logic gates are needed? Can anyone tell me? What other logic gates are needed? Two half header, that is fine.
Sir, AND gates.
How many AND gates?
Sir, 4.
Four AND gates. Perfect. 1, 2, 3, and 4. So 4 AND gate will be needed for this purpose. So 4, yeah, so let me write it properly. So we need 4 AND gate and 2 half adder. Okay, so this kind of circuit is needed. Now let us try to make the circuit of this multiplication. Okay, so the first, let us start from this point. We need x naught and y naught. So suppose I have a x naught and y naught, and I need one AND gate. So this point, that will give you the p naught. Okay, so this is the first term which we have done. Second term, what we need, I need x1 and y naught. Okay, so I need, here I have a x1 and y naught we already have. So I need one AND gate that will give you the x1 y naught. Okay, third term is, again we need one more AND gate, that is the x naught and y1. So x naught is here and y1 is the new term. So this point, at this point I will get x naught y1. Okay, now the next term is, we need one, because see, I have to add this number with this number. So I need one half header, and the sum, whatever the sum will be there, that will be nothing. This is the p naught, and the carry that is generated, that will be summed with the results which we are getting after x1 and y1. So we need one more AND gate, and that x1 and y1 will be ANDed. So at this point I will get x1 and y1. Okay, and this term and the carry which was generated over here, this was the carry. Okay, this will be added, and we need one more half header for this purpose. So one half header will be required, and this carry will be added with the x1 y1. Okay, and the results whatever we will get, that will be the p2 and the p3. So p2 and the p3, this will be the results, and this is how we can simply design the multiplier or the binary multiplier. Okay, so if you have any doubt on at any stage of time, you can let me know. I will explain it again. Okay, so this is how this much of simple the binary multiplier was. Okay, similarly, the similar procedure can be followed for 3-bit multiplication. Suppose I have a number something like x2, x1, and x0, and if I want to multiply it with the, let us assume only two numbers, y2 and y1, y1 and y0. Okay, so suppose this is a number. So what do you need to do? Simply the first term will be y0, x0, second one will be x1, y0, third one will be x2 and y2. So this is all about you will get here. Then you need to multiply y0 into x0, then y0 into x1 plus y0 into x2, and y1 into x2, and then you will do the same kind of addition, and you will need half adder and other things. So now can anyone tell me how many half adder, like suppose I have to find the product of this number. Okay, this is the number which I want to find the multiplication. Can anyone tell me how many gates are needed, and how what are the different hardware needed to implement this one?
Sir, two half adder and one full adder.
Two half adder, one full adder. Okay, what about AND gate? How many AND gates are needed?
6.
6 AND gates are needed? Yes, perfect. Because see, if we talk about the first term that you will get, that will be like x0 y0. Second term will be like x1 y0. Third term will be like x2 y0. And similarly, you can do for this one x0 y1, x1 y1, and x2 y1. So now you need to add here. So this will be reflected as it is. This will be reflected as it is. So see, now we got 6 half header. This is perfect for this. Sorry, 6 AND gate. This is perfect for the product terms. And if we talk about the half header, so let us see how many half headers are needed. So this will be reflected as it is. This is what we will add. So because there is no previous carry, so half header will be sufficient for this purpose. Okay, now one carry will be generated that will come over here. So for this purpose, you need one full adder. Okay, so 2 terms are already there and one carry will come. So one full adder will be required for this purpose. And now there may be some chance that carry will be generated and that will come at this point. So one half adder will again required. Okay, so yeah, absolutely correct. 2 half adder, one full adder, and 6 AND gate is required for this operation. Okay, so this is how you can do that. Okay, anyone has any doubt on this at this point? If you have, then you can ask the question. Otherwise, we can move ahead with the next kind of operations. Okay, so similarly, just like we did for the binary multiplication, we can also perform some division operation. Okay, but in division operation, it is not just like what we did in the decimal. So we need to find something different. Let us see what are those possibilities, that how we can do. Yeah, so the binary division is the another arithmetical operation that we should know, and we should understand how we can divide 2 numbers, one number from another one. Okay, so suppose I have a number which is y1 and y0, and second number which is the x1 and x0. I want to divide, like I just wanted to perform something like this: y1 y0 divided by x1 x0. So this is the operation which I want to perform. We know that, like suppose if I have to multiply it, so what I need to do, if this y1 y0 is greater than the x1 x0. Okay, if y1 y0 is greater than x1 x0, then what will happen? I will this q1 will become 1, and I will write it over here, and I will subtract it. Okay, and after subtraction, whatever the results I will get, that will be the remainder, and there will be no borrow. Okay, so this is what we do. Like suppose I have a number which is 5 and I want to subtract from 3. So what will happen? I will write 3 over here, 3 ones are 3, and then that will remind, like the remainder will be 2 only. Okay, so this is what we get. But what happens if I have a 3 and I have a 5? So in that case, what I need to do? This is not possible. So I need to take some borrow. Okay, so let us assume I am taking the borrow, like it becomes a 13. I'm just taking the decimal value, just for simplicity. Okay, so 13, then I can make it like 5 to like 10, then the remainder will be 3. So there will be some borrow of 10, something like that. Okay, so the important thing is, like I need to check where the borrow will come and at which state the borrow will not come. So if yeah, one more important thing, if like y1 is y1 y0 is greater than x1 x0, then I need to subtract it in, and I will get the remainder, and the borrow will become 0. Okay, and if the borrow is becoming 0 and this particular number, whatever I have x1 x0, is perfectly that we can subtract it from the y1 y0, what it means, the q1 that should be 1. Okay, so q1 should be 1. We can make the division once, like y1 y0 minus x1 x0, and this is possible. So this q1, like quotient, will be 1, and the remainder, this borrow will be 0. Okay, and similarly, if you see the opposite case, if this x1 x0 is greater than y1 y0, and if I'm trying to subtract it, so in that case I need to take some borrow. So borrow will become 1, okay, and then I will get some difference over here, okay, and then difference will be here, and because this is the bigger number, this is the smaller number, so initially this is not divisible, so I need to put 0. So again I can say this borrow is opposite to this q. In the previous case the borrow was 0 and the q was 1, and here if the borrow is 1, then the q will become 0. So the borrow and this quotient will be opposite to each other always. Okay, so let us try to make some algorithm on that, and we will try to design a circuit which can divide these two numbers. So the first thing is like suppose we have a number which is like the first operation that I need to perform, y1 y0 minus x1 x0. Okay, and I'm assuming that I want to divide, like I need to perform this operation. So the first thing is y1 y0 minus x1 x0. The second operation could be I need to check whether I have generated some borrow or not. Borrow is required or not. If borrow is required, okay, like here, if borrow is equal to 0, like whatever the borrow was there, if it is 0, in that case means the it simply indicates the y1 y0 is greater than x1 x0. And if it is like that, then the simply whatever the remainder is, this is nothing but after subtracting x1 x0 from y1 y0, that will become the remainder. Okay, but if we talk about the opposite case, if no, like if the b1 is not equal to 0, or by default it will become 1, in that case whatever the y1 y2, that number will become the d1 d0, because we are not going to subtract it, like we are it is not divisible, so I need to keep 0. Okay, so in that case what I need to do, this q0 will become the b1 complement. I just told you for the both cases, if the b1 is equal to 0, in that case q1 will be 1 because this is completely divisible, and if b1 is equal to 1, in that case q will become 0. So these both are the complementary in nature. So whatever the borrow is, status of borrow will be there, that if I am complementing it, then I will get the q0. Okay, so this is a simple algorithm that can be applied, and the same thing will repeat it for the other number. Let us assume I have a number like y2 y1 y0, and I want to divide it with the x1 x0. So I need to first start from here. So x1 x0 will be there, then I need to follow process, then y0 will come over here, and something like that, the same procedure what we use for the decimal number system. So we need to repeat this one until we cannot finish all the numbers on this dividend. Okay, so this will be repeated. Okay, so this is what the simple procedure that we can do the division of two numbers. Now let us try to, based on this algorithm, let us try to design the circuit for the binary division. First thing what we have done here, the first thing is we have simply y1 y0 and x1 x0. So these are the two numbers, and then I want to subtract these two things. Okay, so let us see here. I have the first number, which is the y1 y0, the second number x1 x0, because see here I am subtracting x1 x0 from y1 y0. So the first digit will be subtracted, and there is no borrow that was previously we had. So for that purpose, for the first digit means y1 and x0, I need a half subtractor. Half subtractor will be sufficient for this purpose. That is why I have used the, for x0 and y0, I have used the half subtractor. Once this number is finished, like we have subtracted this x0 from y0, then there could be possibility that borrow can be generated over here. Okay, so there is two possibility. Then difference is one of the output, and the second output could be the borrow, which is given over here. So that borrow must be connected to the next one, and that is why we need one full subtractor for this purpose. Okay, then x1 y1 and this b0 will be considered for this full subtraction purpose, and that will give you the b1, which is the borrow after the second digit, whatever we have over here. Okay, so this is what is the first stage. Okay, how we can simply subtract x1 x0 from y1 y0. Now once we are ready with this one, so I need to check these two things. This condition need to be checked. Okay, if b1 is equal to 0, let us assume if b1 is equal to 0, so what is the difference? Difference is nothing but this is the y1 minus y2, whatever the difference we are getting, that must be passed to the d. Okay, d1 and d0, whatever the difference we are getting, that should be passed immediately. Okay, but if we see here, if the borrow is not is equal to 0, if the borrow is equal to 1, in this case x1 x0 does not play a role. I have to simply consider y1 and y0. So now if we see here, borrow in this case becomes the control signal. b1 becomes the control signal that decides whether I have to consider this as a d0 d1 or only y1 y0 as a d0 d1. Okay, so if borrow is equal to 0, then whatever the subtraction results we got over here, that will be forwarded. And if borrow is equal to 1, in that case only y1 and the y0 will be forwarded at the output. Okay, so we have two paths, two things that we can decide. Either I can decide this difference, okay, or I can decide this y1. Okay, so the difference in y1 that is decided, and the b1 will play a role to select the path. Okay, so to design these things, let us see what kind of logic circuit is needed. Okay, let us see. Let us consider the first case. If I'm considering the b1 is equal to 0, and that is true, in that case, whatever the sum we are getting over here, difference we are getting over here, that difference will be passed to the d. Okay, so what difference we got here, that difference will be passed through it, and this will be controlled with the help of borrow, because I need to pass this logic if b1 is equal to 0. So to make this logic should be passed, I need to complement this b1, like I need to make the b1 complement. So here b1 was 0, so b1 complement will become 1, and that will activate this particular thing, and accordingly whatever the difference was there, that will be passed at this stage. Okay, so the if b1 is equal to 0, and that b1 is equal to 0 will decide this difference will be passed at this point of time. Okay, now let us talk about the opposite case. Okay, if the b1 is equal to 1, so only y1 and y0 should be passed. Okay, so can anyone tell me how the logic circuit will look like for the second case? How the logic circuit will look like? Where will be the control elements and where will be the connections? Anyone? You are able to understand or not? I don't know. Okay, so no one is responding. Why? I think all have gone to the mall. Huh? Is it?
No, sir.
Yeah, so try to acknowledge the
No,
things.
sir.
Yeah, tell me, what will be the second logic? Is this first logic is clear or not? Like b1 is equal to 0 in this case, why we are deciding like this, how we got to know like this. So this, see, y1 y0 is coming like this component is nothing but this is the y1 minus y0, and this component is sorry, y1 minus x1, and this is nothing but y0 minus x0. Okay, so we got like this. So the next will be like, if see, this was controlled with the help of b complement, because b was 0, and in this case we were getting like d1 d0 is equal to y1 y0 minus x1 x0. Okay, so that is why we complemented it, so that, because see, this is the AND gate and this will be by default 1, and whatever the logic we will have, that will be passed through this one. Now let us talk about the second case. Second case is like if b is equal to 1, b1 is equal to 1. b1 is equal to 1 means in that case only y1 and y0 will be selected. So see here, and this is nothing
In
but
this case, we can consider directly passing B1 with multiplication of Y1 minus X1 and B1 complement with this other one.
okay, like this.
Yes, sir.
Okay, so we will need, like I need to pass this y1 directly, and the b1 will act as a control signal that will allow to pass this y1, and similarly this b1 will act as a control signal that will allow the y0 that will be passed through it. Okay, so in the both cases, like whatever the b status of b is there, based on that I will get two different sections over here. Now because I have I can have, like, based on the status of this b1, either this will be activated or this will be activated. Okay, now if I have to select any one out of it, so what kind of logic will be required, what kind of logic gate will be required?
So,
Either
or
this or this. So in that case, which kind of logic is required? Yeah, someone was saying something.
or gate.
Yes, OR gate. Simply, what is the role of OR gate? OR gate means, like, if this is 0 and this is 1, so 1 will be passed. If this is 1 and this is 0, 1 will be passed. So OR gate means, like, whatever the result I will get, that will be passed through it. So I need to select, I need to use OR gate for that purpose, and that OR gate will be that will give you the actual D0 and D1 differences. Okay, so now the important thing over here is, yeah, this is the complete circuit for the binary division circuit. Okay, now if you see here, if you closely look into this one, these two blocks are nothing but, if you see, let us consider this is one of the input and this is one of the input. So based on the status of this B0, either of one of input is forwarded to the output, either this one or this one, that depends on the status of B1. So based on two inputs and one control signal, here B0 is acting as a control signal, and that is deciding which of the inputs should be transferred to the output. So this kind of logic, we call them the multiplexer. Okay, in detail we will talk about the multiplexer in the next week. Okay, so what is the multiplexer, how to design that, how it works, I will tell you in more detail. But for now you need to know, like, this B0, B1 is acting as a control signal. Okay, and if B1 is equal to 1, then 1 will be transfer, and B1 is equal to 0, then second one will be transfer. Okay, so based on that you can decide, and this is how we are multiplexing the things. So multiple output, multiple input, single output kind of things are called the multiplexer. And we'll discuss it later on. I will talk about the data processing kind of circuits. Okay, now, so this is all about the multiplexer, and the whole block, whatever we can see, this is the binary division. So I'm giving 1 minute time to understand the concept, how I designed this circuit, because this is something different. So based on this algorithm, I tried to design this circuit.
Excuse me, sir.
Yes.
Sir, the one which is in red and the one which is in blue are two different cases.
Yes, yes, that is why I changed the color. Red means this case, and the blue means this case.
Sir, red always mean that B1 equal to 0.
No, not B1 is equal to, yeah. So see here, what I wanted to do. If B1 is equal to 0, so what I need to do, I need to subtract y1 minus x1 and y0 minus x0. I have to perform. Okay, so what it means, if B1 is equal to 0, so I need to pass the subtracted output to the D1 and D0. Okay, so if B1 is equal to 0, okay, if B1 is equal to 0, so I need to pass the subtracted output which I was getting over here. So that is why, because B1 is equal to 0, so the B1 complement by default, it will become 1, and that will activate these two AND gate, and if it is this AND gate, these two AND gates, and that will pass the subtracted outputs. Okay, but if I'm talking about the blue one, in the blue one, what is happening? If the B1 is equal to 1, okay, if the B1 is equal to 1, so it is like this is already able to activate this AND gate, so we don't need to make the complement. Okay, and if it is like that, that will directly pass the Y1 based on this content whatever we have. So I just need to pass the Y1 and Y0. I don't need to subtract it. So Y1 and Y0 will be directly be transferred if this B1 is equal to 1.